Donald Olding Hebb was born on July 22, 1904, in Chester, Nova Scotia, Canada, a picturesque coastal town that would shape the early years of one of psychology's most influential thinkers. Raised in a family deeply committed to education and intellectual exploration, Donald's parents played a pivotal role in nurturing his lifelong curiosity. His father, Dr. Arthur M. Hebb, was a respected physician, while his mother, Clara Olding Hebb, not only taught school but also studied under the renowned Maria Montessori in Italy. Clara's innovative teaching methods, rooted in Montessori's philosophy of engaging with the environment to foster learning, left a lasting impression on Donald. Growing up in rural Nova Scotia, Donald experienced a blend of formal education and outdoor adventure. This combination of intellectual rigor and natural exploration instilled in him a deep appreciation for learning and discovery. He would later draw on these formative experiences in his groundbreaking work on learning and memory. Hebb's academic journey began at Dalhousie University in Halifax, where he initially pursued medicine, following in his father's footsteps. But his passion for philosophy and literature soon led him down a different path. Graduating in 1925 with a Bachelor of Arts in English and Philosophy, he began teaching, a challenging but pivotal chapter that deepened his interest in human behavior. After facing personal tragedy with the loss of his first wife, Hebb found solace in academic pursuits. His journey took him to McGill University, where he began to explore psychology, inspired by influential mentors like Wilder Penfield. Later, at Harvard University, Hebb completed his Ph.D., producing research that would lay the groundwork for his innovative theories. Throughout his career, Hebb made significant contributions to psychology. His focus on the relationship between neural structures and stimuli reshaped our understanding of learning and memory. His influential role as a professor and later as chairman of McGill's psychology department solidified his legacy in the field. A devoted family man, Hebb balanced his demanding career with a fulfilling personal life. He became the first non-U.S. citizen to serve as president of the American Psychological Association, a testament to his far-reaching impact. Donald O. Hebb passed away in 1985, leaving behind a profound legacy in psychology. His dedication to exploring the mind continues to inspire researchers and educators worldwide. The Donald O. Hebb Award, named in his honor, ensures that his contributions will not be forgotten. Moving on to Donald O. Hebb's work and contributions to psychology, Hebb believed that behavior could not be fully understood without exploring the neural mechanisms underlying it, a concept embodied in what we now call the Hebb synapse. He proposed that the brain's structure and function are deeply intertwined with behavior, urging a shift toward a more holistic approach that considers both genetics and environment. In the late 1940s, Hebb conducted an experiment that remains influential today. He raised one group of rats in an enriched environment, his home, where they interacted with diverse stimuli. Another group was kept in standard laboratory cages with minimal stimulation. The results? The enriched group excelled at problem-solving tasks. Hebb attributed this to strengthened neural connections, a concept we now refer to as Hebbian plasticity. This work emphasized that experience shapes the brain, reinforcing the idea that repeated stimulation wires our neural pathways. Hebb's most famous contribution is the idea that cells that fire together wire together. This principle highlights how learning and memory are rooted in the strengthening of neural connections. Hebb introduced cell assemblies, groups of interconnected neurons that process and store information. With repeated activation, these assemblies form stronger connections, providing a biological basis for learning. Hebb didn't stop there. He introduced the concept of phase sequences, which are ordered activations of cell assemblies during cognitive processes like memory recall or problem solving. Think of it as a chain reaction. Activating one memory triggers related ones, allowing us to retrieve complex information efficiently. Hebb's work even paved the way for advances in artificial intelligence. The Hebbian learning rule, describing how synaptic strength changes with simultaneous neuron activation, has inspired neural network models. From basic perceptrons to advanced convolutional neural networks, CNNs, these systems emulate biological processes to recognize patterns, process data, and even mimic human cognition. Hebb also challenged the behaviorist model, which ignored the mind's internal workings. By bridging psychology and neurobiology, he established a foundation for modern neuroscience, emphasizing neuroplasticity, the brain's ability to reorganize itself throughout life. His legacy extends to understanding intelligence, not as static, but dynamic, shaped by experiences and environmental interactions. Hebb's emphasis on empirical research solidified psychology's place as a rigorous science, encouraging future researchers to explore the intricate relationship between the brain and behavior. Donald O. Hebb and his theories still have a lasting impact on today. Let's start with active learning, a teaching approach inspired by Hebb's principles. Active learning encourages students to engage directly with material through discussions, group work, and hands-on activities. For example, instead of simply lecturing about chemical reactions, a science teacher might have students conduct experiments. This approach allows students to connect theoretical concepts to practical applications, reinforcing their understanding. Research supports this strategy. A study by Freeman et al. 2014 found that students in active learning environments perform significantly better on exams compared to those in traditional lectures. Moreover, these methods reduce failure rates in STEM courses by about 30%, showing the profound impact of active engagement on student success. Another Hebbian-inspired strategy is collaborative learning, where students work together on projects or problem-solving tasks. This activates multiple neural pathways and strengthens connections related to the subject matter. Imagine a history class where small groups research different aspects of an event and share their findings with peers. This not only deepens understanding, but also fosters communication and teamwork, essential skills for real-world success. Spaced repetition is another powerful technique tied to Hebb's ideas. This method involves revisiting material at increasing intervals to strengthen neural pathways. A meta-analysis by Cepeda et al. 2006 demonstrated that spaced repetition significantly improves retention rates compared to cramming. Educational tools like Anki and Quizlet capitalize on this principle using algorithms to optimize study schedules. These platforms not only boost memory, but also make learning more engaging and accessible. Finally, project-based learning, PBL, aligns beautifully with Hebb's insights on practical application and collaboration. A meta-analysis by Zhang and Ma, 2023, showed that PBL enhances academic performance, critical thinking, and motivation. It's particularly effective in small groups and real-world contexts like engineering or laboratory courses. Sustained engagement over weeks allows students to deepen their understanding and develop meaningful connections. Donald Hebb's contributions to educational psychology remind us that learning is most effective when it's active, collaborative, and spaced over time. By integrating these principles into our teaching strategies, we're not only improving educational outcomes, but also preparing students for lifelong success.